Right. Diving straight in then. We're exploring something pretty remarkable today. The cosmic journey of the very atoms that make up our bodies. You know that saying, we are stardust?
Yes.
Well, this research takes that concept to a whole new level. We'll be examining a study from the Astrophysical Journal letters from December 2024, alongside some earlier research from 2011, all focused on this rather mind-boggling idea of a cosmic conveyor belt.
What's particularly intriguing here is that we're going beyond that traditional understanding of stars.
Okay.
Simply creating elements during their life cycles. We're looking at a more dynamic process,
Right.
a sort of galactic ecosystem,
Mm-hmm.
where these elements are transported across vast distances and timescales.
Okay, so let's unpack this idea of a cosmic conveyor belt, shall we? Before we get into the specifics of the 2024 study, could you give us a bit of background on the 2011 research?
Certainly. In 2011, researchers made a significant discovery. Heavier elements like oxygen and iron
Okay.
could be ejected from galaxies. These elements become caught in currents within what we call the circumgalactic medium,
Okay.
a vast region of diffuse gas and elements that extends far beyond a galaxy's visible structure.
Hold on. I need to make sure I'm grasping this correctly. We're talking about a halo of sorts surrounding each galaxy, filled with elements that were once part of the galaxy itself.
Precisely. Imagine a sort of swirling mist enveloping each galaxy, extending far into intergalactic space. It's within this circumgalactic medium that these ejected elements travel, sometimes for millions of years.
So it's not just about stars forming and dying within a galaxy. There's this whole other layer of movement and exchange happening on a much grander scale.
Exactly. And this brings us to the fascinating findings of the 2024 study. Using the Hubble telescope's cosmic origins spectrograph, researchers studied light passing through the circumgalactic medium of distant galaxies.
Right.
What they found challenged previous assumptions about the distribution of elements in the universe.
Wait, I'm a bit confused. How can a telescope on Earth possibly observe elements in the circumgalactic medium of galaxies millions of light years away?
That's a great question, and it hinges on the ingenious use of quasars.
Right.
Quasars are extremely luminous objects powered by supermassive black holes. As the light from a distant quasar passes through the circumgalactic medium of a galaxy between us and the quasar, the elements within that medium absorb specific wavelengths of the light. This leaves telltale gaps in the spectrum of light that reaches the Hubble telescope. By analyzing these gaps, researchers can determine the types and quantities of elements present in the circumgalactic medium.
Right. So they're essentially using the quasar's light as a probe to study the composition of these distant halos.
Yes, quite a remarkable technique. And what they found in the 2024 study was particularly striking. Carbon, an element crucial for life as we know it, was detected far outside the confines of the galaxies where it originated.
Okay, so not only are heavier elements like oxygen and iron traveling on this cosmic conveyor belt, but lighter elements like carbon are joining the ride as well. But how can something as light as carbon escape the gravitational pull of its host galaxy? I thought it would be trapped within the galaxy.
Previously, that was the prevailing thought. But this new research suggests that the mechanisms at play in the circumgalactic medium are more powerful and complex than we realized. These elements, including carbon, aren't simply drifting passively. They're being actively propelled by galactic winds, supernova explosions, and potentially even the activity of the supermassive black holes lurking at the hearts of galaxies.
So we're talking about a very dynamic environment with forces pushing and pulling these elements across vast cosmic distances.
Indeed.
Tell me more about what the researchers found regarding carbon in particular. How far out did they detect it?
They observed carbon up to an astounding 400,000 light years away from its host galaxy. To put that into perspective, that's roughly 4 times the diameter of our own Milky Way galaxy. It's truly mind-boggling to think about these tiny atoms embarking on such epic journeys. And here's where it gets really interesting. These findings suggest that many of the carbon atoms in our bodies, the very building blocks of life as we know it, likely traveled on this cosmic conveyor belt for millions of years, spending time outside the Milky Way before eventually being drawn back in to form our solar system and ultimately us.
That's pretty extraordinary thought, isn't it? To think that the atoms making up my hand, for instance, might have once been part of a completely different galaxy, millions of light years away.
Yeah.
It completely reframes our understanding of our connection to the cosmos.
It does, doesn't it? And it raises some profound questions about the nature of our existence and our place in the universe, but beyond the philosophical implications. These findings have significant scientific value as well. They offer a glimpse into the intricate workings of galactic evolution and the dynamic interplay between galaxies and their surrounding environments.
So how does this cosmic conveyor belt actually influence the evolution of galaxies? You mentioned earlier that galaxies need a constant supply of fresh material to form new stars.
Yes, that's right. Stars are the fundamental building blocks of galaxies, and they are constantly being born and dying. Each new generation of stars is formed from the remnants of previous generations. However, over time, the material within a galaxy can become depleted,
Right.
leading to a decline in star formation.
So this is where the circumgalactic medium comes in, acting as a sort of cosmic recycling center.
Precisely. The circumgalactic medium acts as both a source and a sink for the raw materials of star formation. When stars explode as supernovae, they eject vast quantities of elements
Yeah.
into the circumgalactic medium. This material, enriched with heavier elements forged in the hearts of stars,
Okay.
can then cool and condense, eventually falling back onto the galaxy, providing fresh fuel for new star birth.
It's a beautiful cycle, isn't it? A sort of galactic breathing in and out,
Right.
with the circumgalactic medium playing a crucial role in regulating the process.
Indeed. The researchers referred to the circumgalactic medium as a train station, pushing material out of galaxies and pulling it back in, facilitating this continuous exchange of matter and energy. It's a wonderfully evocative analogy, don't you think?
It is, rather. But if I may play devil's advocate for a moment, wouldn't this constant influx of material eventually lead to galaxies becoming ever larger and more massive? We don't observe that happening in the universe.
That's an astute observation. And it gets to the heart of another crucial aspect of this research, the eventual death of galaxies. While the cosmic conveyor belt plays a vital role in sustaining star formation, there are other forces at work that can eventually shut down this process, leading to the cessation of star birth and the slow decline of a galaxy.
This galactic death, as you call it. Sounds rather dramatic. What exactly causes this decline?
There are several theories, but one prominent one involves the supermassive black holes that reside at the centers of most, if not all, galaxies.
Ah, black holes, those enigmatic cosmic behemoths that we often associate with destruction and oblivion.
Indeed. While we often think of black holes as relentlessly devouring everything that comes too close, they can also play a more nuanced role in the evolution of their host galaxies.
Okay.
You see, as matter spirals into a supermassive black hole, it heats up and releases tremendous amounts of energy, often in the form of powerful jets and winds that can extend far out into the circumgalactic medium.
So these black holes, which we typically associate with consuming matter, can also expel energy that impacts the surrounding environment.
Exactly. And this is where it gets particularly interesting in the context of galactic evolution. The energy released by these black holes can actually heat up the circumgalactic medium, preventing it from cooling and condensing back onto the galaxy.
So rather than facilitating star formation by delivering fresh material, the circumgalactic medium, when heated by these black hole outflows, actually hinders it.
Precisely. It's a sort of cosmic irony, isn't it? The very objects that we once thought were solely responsible for galactic destruction might actually play a key role in regulating their lifespans, albeit in a somewhat roundabout way. By heating the circumgalactic medium, they essentially suffocate the galaxy, cutting off its supply of fresh material and eventually leading to the cessation of star formation.
This paints a rather bleak picture for the future of galaxies, doesn't it? They're essentially destined to fade away as their cosmic breath becomes shallower and shallower.
It might seem that way, yes. However, it's important to remember that these processes occur over incredibly vast timescales, billions of years in the making. The universe is constantly evolving, with new stars being born and old ones dying. It's a magnificent dance of creation and destruction, growth and decay, and our understanding of it is continuously evolving as well.
Speaking of our understanding, you mentioned earlier that this research also has implications for our search for life beyond Earth. Can you elaborate on that a bit?
Of course. One of the most fundamental questions we grapple with is whether we are alone in the universe. The discovery that the building blocks of life, elements like carbon, oxygen, and iron, are being transported across vast cosmic distances, by this cosmic conveyor belt has profound implications for the potential for life to exist in other galaxies.
Right, so if these elements are being spread far and wide, the seeds of life, so to speak, are being sown across the universe.
Precisely. If this process is happening in the Milky Way, it's almost certainly happening in countless other galaxies across the cosmos. This means that the ingredients for life are not confined to individual galaxies, but are being distributed on a truly grand scale. It's a tremendously exciting prospect, isn't it?
It is, rather. But how does this research inform our actual search for extraterrestrial life?
Well, for one thing, it broadens the scope of our search. We no longer need to focus solely on planets within our own galaxy. The possibility that life could arise in other galaxies, potentially even from elements that originated in the Milky Way, is really mind-boggling.
It is quite. But how would we even begin to detect signs of life in another galaxy? The distances involved are almost incomprehensible.
It's certainly a challenge, but not an insurmountable one. As our technology advances, we are developing increasingly sophisticated methods for detecting biosignatures, telltale signs of life, in the atmospheres of distant planets. And while currently these techniques are primarily focused on planets within our own galaxy, it's not inconceivable that one day we might be able to apply them to planets in other galaxies as well.
So this cosmic conveyor belt not only sheds light on the origins of the atoms in our bodies, but also opens up new avenues for exploring the possibility of life beyond our own planetary neighborhood. It's quite a remarkable thought, really.
It is, isn't it? It speaks to the interconnectedness of everything in the universe. We are not isolated beings on a solitary planet, but rather integral parts of a vast and intricate cosmic web.
Indeed. This research has certainly given me a new appreciation for the profound connection we have to the cosmos. It seems we are only just beginning to unravel the mysteries of our origins and our place in the grand scheme of things.
And this is where it becomes particularly fascinating. These findings also challenge us to reconsider our perception of time and scale. When we talk about atoms traveling for millions of years, it can be difficult to truly grasp the immensity of those timescales.
It's certainly humbling, isn't it? To think that the atoms in our bodies predate our solar system, our planet, even our galaxy in a sense. They've witnessed cosmic events and processes that we can scarcely imagine.
Precisely. They might carry with them echoes of ancient supernovae, whispers of galactic mergers, perhaps even faint imprints of the conditions present in the very early universe.
It's as if each atom is a miniature time capsule containing a record of its epic journey through the cosmos.
Quite a poetic way to put it, and it raises an intriguing question. If these atoms have such a rich and complex history, could we somehow decipher that history? Could we, in a sense, read the stories encoded within the very fabric of our being?
Now, that is a truly tantalizing prospect. But how would we even begin to access that information?
It's certainly a challenge, but not necessarily an insurmountable one. One avenue of exploration lies in the field of isotope geochemistry. You see different isotopes of an element have slightly different masses due to variations in the number of neutrons in their nuclei. These variations can arise from the specific processes involved in their formation.
You mentioned isotopic ratios earlier. Can you explain to me what those are and how they might reveal clues about the origin of our atoms?
Certainly. The isotopic ratio refers to the relative abundance of different isotopes of an element. By studying the isotopic ratios of elements within our bodies and comparing them to the ratios found in different astronomical objects, we might be able to discern subtle variations that hint at their extragalactic origins.
So, for example, if the carbon in our bodies has a slightly different isotopic ratio than the carbon typically found in the Milky Way, that could suggest it originated in a different galaxy with a different chemical history.
Exactly. It's a bit like a cosmic fingerprint. Each galaxy, each star, each cosmic event leaves its own unique mark on the atoms it produces. By carefully analyzing these atomic fingerprints, we might be able to piece together the incredible journeys these atoms have undertaken.
It's almost as if we're talking about a new form of archaeology, not of ancient civilizations, but of the very elements that make up our bodies. Astroarchaeology, perhaps.
I rather like that term, astroarchaeology. It captures the essence of this endeavor beautifully. Who knows what secrets we might uncover, what stories these atoms might tell us about the universe and our place within it. It's a truly exciting frontier of scientific exploration.
Well, on that note, I think it's time for us to wrap up this deep dive. We've covered an incredible amount of ground today, from the mind-boggling journeys of atoms across galaxies to the profound implications of these discoveries for our understanding of life, the universe, and everything. It's been a privilege to delve into these concepts with you.
The pleasure was all mine.
And to our listeners, thank you for joining us on this intellectual adventure. We hope this deep dive has sparked your curiosity and left you with a sense of wonder about the vast and interconnected cosmos we inhabit. Remember, we are all stardust, and our stories are inextricably intertwined with the grand narrative of the universe. Until next time, keep exploring, keep questioning, and keep looking up at the stars with a sense of awe and appreciation for the incredible tapestry of existence.